Okay, last video on the homework. So we're starting back up with this same merry-go-round from the previous problem. Um, all this information is the same. Radius, push from rest, angular velocity, 8 seconds. So in the previous problem, we got his angular acceleration, the amount of angular displacement that was changing per time. We also got the tangential acceleration, which is like the linear version of the acceleration as the merry-go-round is being pushed and it's speeding up. Okay. And then this question asks for centripetal acceleration. So centripetal is our acceleration that causes us to change directions if we're moving in a circular path. It's only occurs when we're moving in a circular path. So let's see. We have radius. Do we need velocity? Not necessarily, because we can use this relationship. Okay, that bridge equation that we've looked at, we could substitute it in here because we have angular velocity. Okay, so, and they're asking for the centripetal acceleration at 8 seconds. At that 8-second point, the angular velocity is at a value of 3 radians per second. So we can substitute our omega, we got to square it. So I'm just substituting this for velocity. And this is an equation I showed y'all in class. Okay, r squared omega squared over r gives me r times omega squared. And then r is 2.5 and omega is 3, and I have to square that. So I'm going to have 2.5 times 3 squared is 9. I mean, I already know that. So 22.5 meters per second is my centripetal acceleration. That's my acceleration pointing inward. That's the acceleration that has to do with my changing direction as I move in a circular path. And so 23 is a choice. So we'll take that one. Okay. Same merry-go-round. All right. So this is another one that we've not talked about enough that we need to go over some more, but we just have so much to cover in this unit. Same merry-go-round, same radius, same angular velocity, initial and final, same time, total linear acceleration. So in the case of an object that is moving in a circle and it is speeding up or slowing down, so it has got an angular, it's got angular acceleration. It's also got a tangential acceleration, and it's got a centripetal. For linear, if we want a total linear, we're actually going to take this, we're going to use this triangle that's formed by the tangential acceleration and the centripetal acceleration and get the hypotenuse. We're going to use AT squared plus AC squared equals, I'll just call it A total linear squared. So I'm using A squared plus B squared equals C squared. This is to get the combined total of these two vectors. Angular acceleration, our alpha, is separate because that's in radians. That's an angular measure. Okay, these two are both meters per second. So they're more of a linear measure. And if we want to combine them, they're perpendicular to each other, so we can use the Pythagorean theorem. I know that's a lot. Okay. Let's go back and see what we got before. So tangential, we got 0.94. So we're going to have 0.94 squared plus centripetal, we got 22.5. So we're going to have 22.5 squared, and that's going to be equal to our A total linear squared. So let's see, 0.94 squared plus 22.5 squared gives me 507. And that's not my final step. My final step is to take the square root of 507 because that's how I can get my total linear and I get 22.5. Is that right? I guess that's one of the answer choices. So really, I mean, this is a small contributor, as you can see, to the total. The total is mostly the centripetal acceleration to my total. So square root of 507 equals 22.5. And that's, again, going to be meters per second. And that's my total linear. Okay. That's not one that you're going to use as much, but you should be familiar with its existence. Okay. And it's one that I'll include on an equation sheet, for instance, that we might go through, later on next week as we're starting to think ahead to the test. All right, last one. We've got a wheel that's rotating around a fixed axis. So it's got an axis of rotation. And it's got an initial angular velocity of 20 radians per second. During a 5-second interval, so time is going to be 5, the angular velocity increases to 40 radians per second. How many revolutions does the wheel turn through during the 5 seconds? So anytime you see anything like how many revolutions, how many radians, how many degrees, those are always a displacement. Displacement for rotational bodies is an angular. Okay, so we want to know how many revolutions did it turn through. Okay, so we've got to get displacement. Looking at our choices here, we don't know acceleration. So this is going to be a several step problem here. All right, so 1, we need to get the angular acceleration. We can do that using this equation because we've got final and initial angular velocities and we've got time. So 40 equals 20 plus 5 times alpha. I'm going to subtract the 20 from both sides, so I get 20 is 5 times alpha, and so alpha is going to be 4 radians per second when I divide both sides by 5. Oops. Okay. Then I can get my displacement, and I can use this equation because now I've got acceleration. Right? I know time, I know initial angular velocity, I know acceleration, so I'm just going to plug in numbers. 20 is my initial angular velocity, 5 is my time, plus 1/2 times 4 is my angular acceleration I just got, times, again, time, 5 squared. So that gives me 100 plus 1/2 times 4 is 2 times 5 squared should be 50. So 150, that is going to be in radians. Okay. And that's fine if they just ask for like the angular displacement, we can stop there. They ask for revolutions. So we got to convert. So remember we talked in class the other day about 1 revolution. That's 1 time around a circle is going to be 2 pi radians. So if I've got 150 radians, divide that by 2 pi to give me revolutions. And let's see, 150 divided by 2 times pi. Where is pi? Oh, no. Hang on. Start over. 150 divided by 2 times pi in parentheses equals 24, roughly, 23.9. So almost 24 revolutions. So that's how many times it went around a full rotation during this time interval where it was speeding up from 0 to 40 radians per second. No, 20 to 40 radians per second. Okay, So that's all the homework for last week. There'll be some for this week.